Okay. First of all, can you hear me all right? Yes, fantastic. Okay, so I would like to start by thanking the organizer for the opportunity to give these lectures. It's very nice to be here. That's the first time I'm here at GGI. So in these lectures, I will start by giving an introduction to scattering amplitude. So if you want to have a title for the lectures is okay, and more or less, when I prepare for this lecture, I sort of divided that in five, well, since it's five and I'm supposed to give 7 lectures, it's 5 chapters, let's we call this. So just to give an overview, the first part will be an introduction to spinorilicity. Which is one of the formalism behind modern progress in modern scattering amplitude calculations. I will then move on, presumably or hopefully later this afternoon, on 3-level techniques. I then will mention supersymmetry and superamplitudes. Namely, and I will then discuss a bit unitarity methods. For loop level amplitudes. And finally, the last chapter is amplitudes in gravity. Where I would like to talk about recent work on the topics of color kinematics duality and the double copy constructions. Okay, so as you can see, or as you can probably guess, this is a very broad overview of what is actually a large, very large and growing field of research. So for I will try to provide an introduction which is as elementary as possible. And I have put some references on the website for on the page for this particular course. In particular, there is a textbook which is excellent and would strongly recommend, Elvang and Wang. There's also some lecture notes by Lance Dixon, Calculating Scattering Amplitudes Efficiently. And towards the last topics here, there is a review I wrote with some colleagues, which is titled The Duality Between Color and Kinematics and Its Applications. Aside from this, and I think it should be by now on the page of the course, I've also created a shared Google Doc folder in which I will share some material. And in particular, at the moment, there are some chapters, some sample chapters of a book I'm in the process of writing with the same people with whom I have written the review, The Duality Between Color and Kinematics and Applications. So you get to see a preview of some of the chapters of that book, and please let me know what you think about that. I should say that the way I lecture, I would like to welcome questions, so feel free to interrupt me at any point in time. And if you have questions you prefer to ask via email, this is my email. In particular, if you have comments on the book chapters, just let me know even after the course. Okay, very good. Regarding the format of these lectures, actually, I am told that I have some flexibility now to use this time. I was thinking about lecturing for 45 minutes, give you 10, 15 minutes break, and then lecturing. Unless there are preferences or strong feelings for the contrary. I think it's good to have a break, get a leg stretcher after a while of lectures. Okay, very good. Any questions before we start? So then I would like to, well, to start from the first chapter. So let me just start by a little bit of on the way of motivation. So why do we care about amplitudes? Scattering amplitudes are closely related to experiment. This is something that you have seen, I presume, in introductory quantum field theory courses, but experimentally observable quantities, namely the differential cross-section, is closely related to the amplitude in the sense that the differential cross-section admits an expression in which we have our amplitude here, and our amplitude is, of course, a function of certain things, which I will explain in a second, but say scattering data, momenta, polarization of whatever I am scattering. We take the square of the amplitude, and this is almost the differential cross-section in the sense that there is a kinematical part, the Lorentz invariant phase space for the particular scattering event which we are considering. So there is a very close relation between the two. There is, of course, a kinematical part that depends really on what kind of event I'm considering, and then the physical information, how things interact, is captured by the object of the scattering amplitude, or more properly, by its square. So a lot of times you'll hear people saying that scattering amplitudes are observable quantities. That's almost true. They are very closely related to something that can be observed, at least in principle. So the standard technology for calculating scattering amplitudes relies on Feynman diagrammatics. Feynman diagrams are great for understanding the general properties of amplitudes from deriving some of those properties, but they are typically hard to calculate computationally. And this is something that I will try to provide a little bit of a justification for. So over the years, methods have been developed for calculating the amplitude here that circumvent some of the limitation, the computational limitation of Feynman diagrammatics. And this is what this mini course will be about. My plan is to start more or less where your average quantum field theory course stops. So I will assume certain things from a quantum field theory course. So perhaps it's a good moment to sort of mention or review what I will assume. And I hope that you agree that it's a reasonable set of assumptions. First, of course, I will assume, or I have already assumed, rather, that the relation between cross sections and amplitude is something you have seen before. And I see somebody's nodding, which is very good. I will assume that given a Lagrangian, if I give you a Lagrangian, you are able more or less to get the Feynman rules, which is relatively straightforward process. And also I will assume familiarity with simple Lagrangians or simple theories that you have already encountered. So for example, a scalar field theory, Yukawa, QED, QCD, mostly QCD. And I will also assume that you have already seen or accepted some of the objects which appear in the definition of non-abelian gauge theory. Representation matrices, structure constants. In some cases, I will give you some reminder about some facts, however, and some of those properties. I will assume that you have seen word identities as a way of either enforcing gauge invariance on an amplitude or as a consequence of gauge invariance of an amplitude derived from a Lagrangian, which is known to have that property. And I will also have to assume some of the basic facts of quantum field theory fermions. So Dirac equation, some spin-out technology, Grassmann numbers. These are the main things I will assume. And I should mention, I will mostly work in 4 dimensions. And I will use natural units in which h bar c are set to 1. Okay. Questions about this? Anything I am assuming and I should not assume? Okay, that's very good. Okay, so while discussing, while motivating my lectures, one of the things I stress is that Feynman diagrammatics has some limitations. And since this is really key, I would say, to why modern amplitude methods are being developed and why they are necessary, it is probably good to spend a couple of extra words about this. So of course, Feynman diagrams are the standard method technique that you see in a quantum field theory course. So I have to, before giving you alternatives, I have to explain to you why over the years, this method is no longer a state of the art in a sense, or at least computationally, there are some limitations to this. And one of these is the number of diagrams. So if you are considering amplitudes with a large number of external fields or legs, then the number of Feynman diagrams which you need to introduce to calculate the amplitude, which is the well-defined object, right? One of the things about Feynman diagrams is that these are contributions to amplitude, but the individual Feynman diagram does not have a meaning of its own. It is, in fact, some of the physical property of the amplitude do not exist at the level of the individual Feynman diagrams. What I'm saying is that if you want to check, say, gauge invariance, you have to put together all the Feynman diagrams. Individual Feynman diagrams are not by themselves gauge invariant. So this number of diagrams grows very quickly. And if you are interested in amplitudes which are, say, beyond 3, 4, 5 points, this will be some major problem we'll have to face. There's a nice example, actually. How quickly do Feynman diagrams grow? Well, let's consider a theory, for example, that has only cubic diagrams. And again, as I said, I mean, Feynman diagrams are perfectly good if you want to do 3, 4, 5 point amplitudes. But to say that you want to do an m point amplitudes. Wait. Then, how many diagrams do you need to add up? Actually, there is a very nice little exercise in this calculation for getting an m-point result on the number of diagrams. And I should say here, this is whenever I am taking something from a source which is not the one I put on the website, let me just say that I'm taking this example from the Tazi lectures on amplitudes. And I give you the preprint number so you can consult this. This is Clifford Chung lectures a few years ago. There's a very nice example on how to compute this. And while this example is in a sense slightly orthogonal to some of the material which I will cover from now on, I think it's such a nice example that I feel compelled to give it. Namely, there is a trick which we're going to employ to counter the Feynman diagrams. That is, we're going to consider a toy model in which we have a purely algebraic kinetic term. So let's consider a theory with a Lagrangian, and this is, of course, is not one of our theories that I mentioned before that we are actually really interested in calculating amplitude, because this is a nearly trivial theory in which we have a Lagrangian, which is, there is no derivatives, right? So this is purely, as purely algebraic equations of motions. And then we note that there is an equation of motion. I mean, just by using the standard Euler Lagrange equation, this theory has an equation of motion which is of the following form. So we have J here is a source, phi is our scalar field, and we have an equation of motions which we can actually solve right away. However, it is also possible to actually express the solution using Feynman diagrams. This is where I'm saying that I'm using methods which are slightly orthogonal to some of the material we'll cover later on. But one fact, which I can motivate in a second, is that a solution of the classical equation of motion can be expressed with the help of Feynman diagrams in the following form. We can have like a summation over Feynman diagrams at or radar endpoint correlation functions. In which we are taking the endpoint correlation function. We are leaving the first variable as the variable of phi, and we are integrating over a series of sources for the other. Okay. And there is a normalization here, which can be explained in a second. So this is where the Feynman diagrams play a role. Essentially, this Gn can be expressed with the help of Feynman diagrams. Which Feynman diagrams? Well, the reason I introduced this theory, or rather I found an example with this theory, is that the Feynman diagrams are very, very simple in this particular case. So if you look and you go to the standard step of Feynman diagrammatics, because this is a toy theory, you find that the Feynman rules are actually, the propagator is 1, and, well, the vertex is lambda. I kept the coupling constant. So what this theory does is essentially counting Feynman diagrams for you, right? Because it will come that all Feynman diagrams here will have weight 1. So this and what I need to do is just look at the nth term in that expansion. Wait, sorry. And I will be able to read off the number of Feynman diagrams, since all the Feynman diagrams come with weight 1. Okay, so how do I do this? Well, I remember that, as I said before, the solution to the standard, to the classical equation of motion here, it is obtainable just by solving a quadratic equation, right? So my solution here will be equal to 1 over lambda, and then there will be 1 minus the square root of 1 minus 2 j lambda. And here I have picking, I mean, of course I have two solutions, a quadratic equation, but I pick the solution such that phi at j equal to 0 is equal to 0, which is the physically relevant one. Then we expand. So we expand this as phi of j. This is just the expansion of the square root I'm using here. Taylor expansion of the square root. There is a 1/2 j first term, and then there is a summation with n going from 2 to infinity, so starting from 2. This is 2n minus 3, double factorial. N factorial 2 to the n. This is the coefficient, and then, of course, we have the x in the Taylor series is 2j lambda, so this is a 2j at the n, and then lambda at the n minus 1, just because I divided by lambda here. All right. Upon shifting of n, this is the answer to my question of how many Feynman diagrams I have. So, for example, 2 to the n simplifies here, obviously. The result is, so keeping in mind that hang on. So this is equivalent to a Gn in which we are having 2n minus 5 double factorial lambda at the n minus 2, where the summation, I have shifted the summation of n. Okay, so hence the number of diagrams at n points is 2n minus 5 double factorial. So we have a factorial growth for the diagrams. Let's remember this magic number for the future, because some of the techniques I'll have or I will present are based on cubic graphs, and this is the number of cubic graphs at multiplicity n. Okay, how does this sound? Is this reasonable? Do I need to explain why I can build a solution to the equation of motions in the form, what did I put in this form? Is this something you have seen in your quantum field theory course? Or is it something which requires a little bit of explanation? You've never seen that? Okay. Very good. So a little bit of explanation seems to be necessary. So let me see how I can organize myself. Okay, so what you have, I bet, seen in the standard QFT is the generating function for Feynman diagrams being expressed in terms as a path integral in terms of the action and being expressed as the exponential of the generating function for connected diagrams, okay? So the expansion in terms of Feynman diagrams of this object and of this object, it is something you've seen. Is this a reasonable starting point? Okay, fantastic, thank you. Okay, so then there is a series of manipulations which usually in a context of quantum field theory, you do when we are discussing quantum effective actions, but will not be needed in this particular case. In a sense, what I'm presenting here is an overkill because we are just not going to consider quantum correction to our action. Instead, we're just going to stay purely classical. So we define something which will interpret as the classical field as the expectation value of a single field. You know how to do this, right? This is equal to, I mean, if I get my factors of I right, functional derivatives of z divided by z, which is exactly the derivative of w. This is the one-point function. Typically, you set j equal to 0, and the one-point function is under certain circumstances. I mean, this will be the vacuum expectation value in the absence of a form. Here, we'll in the absence of a source, sorry. Here, we'll keep j non-zero. And now, I claim that this object obeys classical equation of motion. Okay, so the first observation here is that this object and this object are the same, right? Because this is the expansion of W in terms of Feynman diagrams. And even the normalization comes from the fact that there is a functional derivative of J with respect to that. So how do you see that this obeys the classical equation of motion? Well, the quick argument, and here I do not know where you're getting your quantum field theory from, so I assume Zrednicki. But there's similar, I mean, there's many textbooks, of course, but let me just give you a reference. This is chapter 21 for some of these manipulations. Again, this if you go check this chapter of Zrednicki, there's way more stuff because it's about quantum corrections. We're just going to consider, so in a sense, we are doing an overkill in using this technology for this. But then the quick argument would be that Z of J, we evaluated this with a saddle point approximation. And what is this? This is the exponential of the classical solution to the equation of motions, where we are having, of course. And here, I would say that this is where the quantum correction enter. But although we will not be interested in those. So this means, I mean, almost trivially, that Wj will be equal to, in this approximation, to the action evaluated at the classical field. Again, classical field means a saddle point, so solution to the equation of motions here, plus ij. Sorry, plus without the ij, phi classical. Okay, and we note that phi classical is a function of J, right? This is a solution to the equation of motion in the presence of a source, J. So it's a function of J. Now, let me see what I can cancel. So at this point, we will just look at the object obtained as the functional derivative of the generating function of connected graphs, so W, with respect to one of the sources. So you evaluate this, and this you get, well, the derivative with respect to the action by just using that. And J also, and then there is the derivative, of course, of the classical field with respect to the source, but this is equal to 0 because of the definition, because it's a saddle point, because it obeys the equation of motion, and what you have left is phi classical, thereby justifying the identification up there, the expression on the first line over there, which is indeed what I have used for computing this. Okay, and now W can be expressed in terms of Feynman diagrams. All these Feynman diagrams come with a weight 1, or if you prefer, lambda to the n minus 2, where n is the number of points. So I can use Feynman diagrams to construct classical solutions. This is sort of an aside, I don't know, bonus, if you like. Let me just mention that this usage of Feynman diagrams to construct classical solution has a name, the Perturbiner method. And I have, in a sense, established or motivated like the result I wanted. The number of diagrams at endpoints grows factorially with the multiplicity or according to this formula over there. So in other words, it would be nice to be able to express amplitudes or more in general object coming from Feynman diagrams in a way that circumvent having to consider all these individual contributions. This is the number of the factorial growth in the number of Feynman diagrams is only one of the limitations. Of the limitation of Feynman diagrammatics. There's also others. A further complication is dependence from kinematical data, from the epsilon, the polarizations, and the momenta, which puts you in a situation where it's not that each individual diagram is 1 or lambda to the n minus 2. Instead, we are in a situation in which complicated expressions of polarization and momentum needs to be evaluated. If you consider QCD, if you consider Yang-Mills, I cannot honestly say that it is that complicated, although it builds up. If you consider gravity, it is. So there's also this element of complication. And when I discuss gravity in the last chapter, I will also point out, give you an example of this complexity. But there's a lot of information attached to individual Feynman diagrams. And often individual diagrams have complicated expressions, but you have cancellation between different diagrams. An example of this is word identity. So if we have an amplitude, and let's assume here that we have an amplitude with some vector fields, and word identity tells you that if you replace the polarization with the momentum of the corresponding external field leg, the amplitude is equal to 0. But then you look how this relation is obtained. How do you get the 0 in practice? This 0 is the result of cancellation in between different diagrams. So this tells you really that what is simple and physical is not the individual diagram, but is the sum of diagrams. Individual diagrams by themselves are not physical. So given these 3 points, an approach has developed itself in the field of amplitudes about bootstrapping amplitudes. So bootstrapping amplitudes is, in a sense, the construction of amplitude. There's oftentimes the word bootstrap. I mean, being in a school on theoretical physics, I guess you hear the word bootstrap quite frequently. And in this particular context, what I mean is the construction of amplitudes directly from first principles. Unitarity, locality, gauge invariance. So in the particular case of amplitudes, some of these first principles, as I said, are unitarity, locality. Gauge invariance will be one of the list. And then oftentimes I'll have to start somewhere. So in this particular case, I will start from simple building blocks. For example, amplitudes at 3 points. In most cases, it could be amplitudes that are low multiplicity. I mean, you can have some theories in which you start having the first non-trivial amplitudes at 4 points. And this is an interesting, in a sense, philosophy in that it tends to replace Lagrangians. So instead of using the Lagrangian to define a theory, you'd use these simple building blocks. And I can tell you I have this theory with amplitude at 3 points. I assume these properties, and I try to obtain formulas, of course with some caveats, with some string attached in a sense, for amplitudes at first 3 level, higher multiplicity, and then eventually loop level. What is interesting here, and this will be a recurring theme in this lecture, will be that I still assume that the Feynman diagrammatics exists and makes sense, but I will use it instead of doing the brute force calculation for inferring some of the properties of what the result should be, and then use physical principles to fix that result. I will provide examples of this, but for now, please appreciate that there is this, in a sense, ambition about trying to use Lagrangians as little as possible, and yet the fact that I have a Lagrangian, the fact that I have a path integral, the fact that I have a Feynman diagrammatics will be used but will be used in a sense in a smart way rather than just doing the brute force calculation. Okay, so how do we do this? Well, the foundation of that will be the first chapter, as this was an introduction, namely with spin-realistic variables. And I will, in the second hour of this lecture, proceed to illustrate examples on how we can organize the kinematical data defining our amplitude, namely this P and epsilon, in a way that manifests the underlying simplicity. Is there any question about what I've done so far? Yes. Yes, correlation function I've used are at 3 levels. And let me see, is it still there? So I wrote quantum correction over there, right? So you want to have a quantum correction, then you take away the 3 level. And if you go and read the chapter of Zreniki that I recommended to you, Zreniki doesn't care about 3 level, he wants to do the quantum effective action. So in a sense, I'm using here, I have not been fully, shall we say, honest in requiring, I mean, what I just put on the blackboard is not normally part of the standard quantum field theory course. But in a sense, what you see in the standard quantum field theory course is a bit more advanced. So it is, this is why I felt comfortable, at least, attempting even this in the way of motivation. So if you want to do the quantum action, then you have to start, well, I don't know. So in the saddle point approximation, you are going to have not just the exponent evaluated at the classical solution of motion, right? You're going to also have a determinant. Surprise, that's the first correction to the quantum effective action. And then you have to go forward and start computing also diagrams. But what the usage of this result I've had here involves only 3-level diagrams. And it's built for building solution to classical equations of motion. Yes? Yes. No, this is not, by no means, it's not a stupid question. Yeah, I do not know, really, because what you can think about this in a minimalistic way, which is the following, right? Yes, it's dependent on how, I'm not going to forget what I've learned in quantum field theory. Just simply, instead of rushing to actually calculate all the Feynman diagrams, which is a mess, I will just try to constrain the result, which is something we do in theoretical physics all the time, right? You know, somebody said, never attempt a calculation in theoretical physics if you don't know the result. Here is like, okay, Feynman diagrammatic works. Of course, nobody forgets quantum field theory. But what can I say about the form of the result? Can I constrain that from, for example, a very simple example, and again, keep in mind that this is something I will return to, so I'm not supposed to, I mean, I will provide explicit examples of this, but obviously you look at the Feynman diagrams and you know where, you look at an amplitude and you know where the poles are, right? Feynman diagrams has propagators in precise locations. You can have a pole which doesn't correspond to a propagator, like in the denominator going to 0 in the propagator. So I know this is very important, though, because I have some information on the poles of my amplitudes, even without throwing in the precise expression for the vertex. This I can use. The fact that Feynman diagrams exist doesn't mean that I have to use them to get my amplitude. If I can get the amplitude in a shorter way, perhaps recursively, then I should use that. If you ask the question to someone else, they could say, well, you know, we would like to replace completely Lagrangians. That would not be my answer, but it is also a possibility. So there is some tension in here. There is an attempt on sort of reformulating everything, but this attempt of reformulating relies a little bit on the old formulation. Okay. I would suggest that we get a break until 10. Is this acceptable? In case any of you has questions, I will stick around, at least for part of this break. So stretch your legs, and we will continue at 10. Sure, just a second, okay? Let me. sono... cioè è un effetto che ho... È un effetto che ho sul... Probabilmente non so. Ok. Sì. Ma cioè, mi dici quando fa... sì, è acceso, è acceso. È acceso. Sì. Ma sembra, comunque sembra che vada, cioè, la visuale è molto buono. Sembra che vada bene, quindi direi... Poi tutte e quattro le lavande, bello comunque. Ok. Sono in fila per il caffè comunque. Sì, è vero, no, però che devo fare? Cioè, no, ma sono troppo veloce, sono troppo lento? 10 minuti accademici. Vabbè. No, io non... Sì, vediamo. No, sono... Sì? Ok. No, questo può funzionare. Ok, ottimo. Ok. Thank you. Okay, very good. So we are ready to start again. Hopefully. Okay. So next, the next topic I would like to discuss, or if you wish, the beginning of the technical part of this lecture is the spinor helicity formalism. So we should think at this formalism as a way for obtaining compact expressions for scattering amplitudes. And after I illustrate how this formalism works, I will also have some words on why you end up getting simple expression for amplitudes together with a first example incarnation of this bootstrapping principle. So the starting point for this is a particular way of writing physical for momenta. So we start having physical the momentum of, well, for us is going to be one of our scattering states. So this is the part of the kinematical variables from which the scattering amplitude will depend, and we contract this with a so-called sigma matrix. This will be some matrix. If you want to see what the component of this matrix is, it is something of this form, where these are the components of the momentum, P1 plus IP2, and here you have P0 minus P3. So essentially these sigma matrices, which, yes, you have seen before, are like the identity for sigma 0, or the Pauli matrices. And we are in a sense representing this momentum with a 2x2 matrix with complex entries. Okay, so if you calculate the determinant of this matrix, let's see, P alpha alpha dot, we would get that is P0 squared minus P1 squared, P3 squared. So in other words, this is actually P squared. And for a physical state, this is equal to M squared. And here, let me just commit or specify my convention about eta mu nu. For me, it's a mostly minus. Okay. And I'll try to follow these conventions as faithfully as I can. I should also mention that my conventions, among the references which I gave, probably follow most closely Lance-Dixon's lecture notes. Okay, very good. So a lot can be said about what is on the blackboard right now. I mean, you can say that actually this is, of course, you're gonna have that you can transform with a Lorentz transformation the momentum. What does this correspond to? Well, this corresponds to a complex 2x2 matrices with unit determinant which act on this matrix on the left and right. And in other words, this is, well, this is part of an isomorphism between SL2C, where to be specific, mod Z2, and the Lorentz group, or to be specific, the orthochronous Lorentz group. For us, this will be a way of organizing momentum. Okay, and we want to focus on massless external particles. This is an important assumption, and I want to be clear that these techniques can be generalized also to massive cases. But what you will see in these lectures are the simplest examples. And also what I'm particularly motivated in doing are Yang-Mills theory and some gravity, in which case, of course, you need to start describing massless fields. So additional simplification can occur in the event in which you are considering massless particles. Because what does it mean? Well, in massless particle, obviously the determinant is equal to 0. So what does this tell you? That either rows or columns, your choice, are not linearly independent, right, in this matrix. So we can write this matrix in a form. So let me just try to write something which can be followed. So the determinant is equal to 0. So this P alpha alpha dot, which I have constructed in this way, can be written in the following way. Can be written as the product of two objects, each one having a different index. This is the statement, you know that rows and columns are linearly dependent, right? If you think that, yeah. Dependent. Okay, very good. So now on the way of notation, instead of using lambda and lambda tilde, I will actually write it in the following way. So I will write the lambda as this cat-looking object with, and I will write the lambda tilde as this separate bra-looking, and notice that there's an angle here and there is a square here. This is corresponding to the fact that we are having two different indices. And this is just a matter of notation. But this will be important for writing complex expressions. So sorry for switching notation right away after introducing the objects. One thing which should be noted is that this decomposition is not unique. Okay, so if I can get the same momentum, if I scale lambda alpha in a way, say t is a parameter here, and I scale the other spinor, this is a spinorial index, so we call it a spinor, in the opposite way, 1 over t lambda tilde alpha dot. So this is something to keep in mind. This decomposition can be done, but there is this fundamental, non-uniqueness of this decomposition. Another thing you may wonder here is that, do you want to impose reality conditions? So are we discussing amplitudes with real momenta? Are we discussing amplitudes with complex momenta? The fact that I'm asking this question may be greeted with a certain amount of skepticism at this point, in the sense that, of course, we're considering amplitude with real momenta, right? Except that when we are discussing the form, the functional form of an amplitude, where does the amplitude have poles? It makes sense to invoke the notion of having a complex plane, therefore the momenta. So at this point, I will be agnostic about whether we really are taking a real momenta or not, because in studying the properties of amplitudes, I will be interested in going to the complex plane. So just note that if the momenta for you are real, there will be some relation between this. If the momenta are complex, there will not be some relation. I will explain you the relation, the behavior under complex conjugation in a second. Okay. Now, it should be noted also that there is, we have Levi-Civita symbols for, and here it should be said always alpha is equal to 1 and 2, same range for alpha dot. That's clear from the matrix. So I can actually define P alpha. So keep in mind that this is as the bra using an epsilon Levi-Civita alpha beta to actually raise the index. So whether it's a bra or a cat, it depends on whether the index or matches the fact that whether the index is high or low. And the same thing will be done with the square spinner, right? Which in this particular case, it would be raised index. And again, this would be equal to epsilon alpha dot beta dot of p beta dot. And I'm using conventions here. You'll tell me how consistent I am at the end of these lectures. In which this is true, the same for the dotted objects. Okay, questions so far? So again, important decomposition. Does everybody understand this? I'm concerned if somebody doesn't understand this, at least operationally. Let's forget about, well, there's many levels of understanding of this formula, but you need to understand this if you want to follow the rest of the course. Okay. A possible question, which I definitely would have, is actually twofold. So first, what is the physical meaning of these objects? Second is, how do they fit in, I mean, we have identified them as spinors, so how do they fit in the conventional, I mean, how do they relate to the chapter of Zreniki or Schroeder or whichever book you have chosen to learn quantum field theory from, in which spinors, particularly gamma matrices, are introduced. So the answer to this question, or a answer to this question, is that we consider that the spinor or the object, I don't know, psi, and we use this sort of put the two different cats as the entries building for, I mean, a Dirac, you would say spinor or a spinor with 4 indices. Okay. Then, if you want to consider the momentum contracted with a gamma matrix, and you use a particular basis of gamma matrix, or you use a representation rather in the gamma matrices in which you have that this is sigma mu alpha alpha dot, and here we put an object defined, to be defined in a second, the barred sigma alpha dot alpha of diagonal, where I have defined the bar sigma in a rather natural way. Notice also the order here, alpha dot alpha, alpha alpha dot, by acting on my unbarred, sort of sigma, beta, beta dot, and raising the indices. So that we have alpha, beta, alpha dot, sorry, epsilon, alpha dot, beta dot here. And this is my definition. So having defined this bar sigma, we build a gamma matrix in this way. I mean, it's a gamma matrix. You can show that actually it obeys the properties of the gamma matrices. And then we can show that we have that the momentum contracted by gamma matrix acts on that object and gives you 0. So these are solutions of the Dirac equation. With 0 mass, of course. I'd be worried if I get a mass out of this. Okay, very good. So this is, in a sense, a physical interpretation, right? I can think about them as either solution to the Dirac equation or spinor polarizations. if you prefer. And in this particular case, let me just say that we take, I mean, a conventional point at least. In a scattering amplitude, we take all particles to be outgoing. Okay, so there's different conventions. Some people prefer to have everything incoming. In general, if you have a scattering amplitude, if you want to have a scattering amplitude with some incoming states, some outgoing states, will be related by crossing with either all incoming or all outgoing. So it is good to write scattering amplitude specializing to this situation. Why do I say this? Because then, if we want in particular to scatter fermions, we have that an outgoing anti-fermion if everything is outgoing, I have something which is an anti-fermion and something which is a fermion. The difference between the two is without a reference to the physical world in which we have, electron and positrons. This is slightly conventional. But the polarization I can use for fermions then will be if the V, so to speak, in the quantum theory textbook will be something of this form. So a positive polarization will correspond to the object with the dotted index. And then we are going to have a negative polarization, which will correspond to 0 and then P alpha. Okay, so this is another way of thinking about that. And similarly, we are going to have the outgoing fermion, which corresponds to a U bar. And here you have a U bar minus P, which corresponds to P alpha dot 0. And we are going to have the U bar plus, which corresponds to 0 and then P alpha. Okay, so these are polarizations which we can use when we are scattering fermions. And before I stop to ask you if you have questions, there is one last thing I want to put on, namely, and I would say most importantly in the sense that this will be the object that concretely I use for expressing my amplitude. There's a very natural bracket between these things due to the fact that nothing more than I have a Levi-Civita symbol, okay? So we can define contractions. And here we have that, say, here I have to explain a little bit about the notation. So a lot of times when I start having different momenta, I'm not going to write pi, pj for different external states. I'm just going to write this as a bracket of I and j with, with the understanding that they will be obtained from the momenta of the corresponding labeled particles. This will be just a pi with the alpha index here, contracted with the pj, with the alpha displayed in this way. Same thing, there will be a natural square. The natural square will be, and the high-low indices here are just a result of what's a bra, what's a cat for two kind of spinors. And I call this, of course, angle and square brackets. And this will be, I mean, concretely, spoiler alert, my expressions for amplitudes will be collections of these brackets. And of course, at this point, we should actually start discussing the properties of these objects, okay? And the very obvious property is that because of the antisymmetry of the Levi-Civita symbol, the antisymmetric epsilon ij, this will be equal to 0. So whenever you have the same particle, you're going to have that the corresponding brackets are going to be equal to 0. Okay, questions about this? So again, the last 5 minutes were the transition between that very important expression for momentum for massless particles to the introduction of these objects, their interpretation as either solution of the Dirac equation, or if you like, fermion polarizations, if I'm thinking about scattering, and then the introduction of the brackets as natural objects. And now the next question becomes, what are the properties of things I can write with these brackets? So a good moment to ask questions. Yes. Yeah. Sorry, yeah, so this is antisymmetric. So yeah, so okay, very good, very good. Very good. So, and then this is the only, I mean, I tell you one entry and you interpret it. There's only one independent entry. Very good, very good. Anything else I've forgotten to put, which is important? Okay. Okay, very good. So let's continue. And now the topic is properties of these friends here. Let me make some room. Okay. So I should just mention that some of these properties, perhaps unsurprisingly, will be used over and over in practical calculations. So some of these I can just quote, but it's always good to spend a second and try to reobtain them, and also to familiarize yourself with the formalism. So one way of doing this is, one of the properties is that, say that now we consider brackets involving two particles, right? Notice the opposite order in here. This is as a very simple interpretation. This is an Sij, where this is the Mandelstam variable. Okay. And I should probably show you why, right? That's a simple manipulation, but should not be considered trivial. So how do we verify this? This actually involves a passage or like a reformulation into perhaps a more familiar territory. So we write this. Eventually, this will depend on properties. So we recognize that this combination J, this is the contraction of the momentum with respect to one of the sigma matrices. So we write this as the ith momentum, the J momentum, contracting what? Well, if you write these in terms of the sigma matrices, then this becomes sigma bar mu, sigma nu. Okay? But then this is perhaps expressed in a more familiar way as putting a chirality projector and then having here, let's just write them in here, pi pj, where the chirality projector was used for going from, this is defined as the contraction with the gamma matrices, and this is just for going from the gamma to the sigma. But then we know what this is, and this should be equal to 2 pi dot into pj, which is indeed Sij. You have seen this identity with a 4, eta mu nu. The reason of the 2 is because of this projector, right? Okay, so this is a simple example of a relation that actually I'll use a certain, a large number of times. Another example of this would be a relation of this form. So namely the fact that if you put a sigma matrix between this, the bra and the cat, it gives you the momentum with a factor of 2. A third relation, which I'll use a number of times, will be also a contraction between the two. I mean, this is, if you like, a Firth identity. So sometimes we will find ourselves in front of the following object. So we are going to have different spinors here, and contracting sigma matrices with the contracture Lorentz index. Now, I tell you the result and then I show you the result. And again, some of these you may wish to verify yourself explicitly. Some of these you just want to box it and use it in the calculation that will inevitably follow. Notice here that this is, there's a 2 showing up and then ik and then lj. So the ordering is the opposite between the two. And I think I want to show you this because it's also a good way of familiarizing ourselves with the formalism. So in order to show this, I need to note the identity. So we have a sigma, say alpha dot, and then we contract this with a sigma mu, beta dot, and this is equal, and this being one of the standard identities, but this being also something you can verify directly. With just a pair of epsilon tensors. Have you seen this identity before? Just to give me a quick. Some people are nodding, but not too many people are nodding. Okay. So a way of verifying this identity would be, well, I know that this thing needs, I want to look for an expression of this in terms of, say, constant here. Then I fix the constant, for example, by contracting both sides with a sufficient number of epsilons so that it becomes a trace, and then I fix the constant in that particular case. Or you can just say, well, this is an identity oftentimes found in the appendix of your favorite book, with spinners, I don't know, Wessenberger perhaps. And I just use this identity. Or you can verify that explicitly, right, by having an expression for one of the sigma matrices. Okay. Once you have done this, once you use this, you can see right away that this identity follows, just by addressing this with a sufficient number of spinors and keeping track of the contractions. Okay. Questions? So just in operational terms, in terms of building some muscles for simple calculations, this will use a lot. This will use a lot. And of course, this will use endless number of times. And also this we will use. Everything boxed, which makes the boxes meaningless at this point. There's one last identity, which is, I'm not sure if I want to say less trivial, but we will use it a lot also. And this is the so-called Schouten identity. Sorry about that. So this is something, an identity which arises when we have a number of spinors of the same kind, involving 4 of them. So we keep, to remember it, we keep one of the labels fixed, say hi, and we use a cyclic permutation of the other 3. So I, K, L, J, plus I still fixed, and then L, J, K, and this is equal to 0. Is this obvious? Well, it's not to me. So this is a consequence of the fact that we note that J, or any spinor really, can be obtained, can be expressed as a linear combination of the other 2. Because these are 2-dimensional spinors, right? I don't have so many independent. I just have 2 independent spinors. Okay. And then we just plug in the expression. So what we get by plugging in we just plug in. Well, okay. So we have the I, and then we have a K here. KL. This is an A. This is equal plus there's a B, and this is IL, right? KL, and then this is plugging in just to the first term. Then we have here there's still the I, the K is fine, and then the J. Well, the J here, there's an L, so we use the fact that the angle bracket of L is equal to 0, so only the term proportional to A remains, right? And becomes LK. And then here we have IL, same thing in here, there's just the B because the terms proportional to A would be multiplied by 0. And here you see that this is LK. What is this though? Well, we have to be These are anti-symmetric. So we see, for example, the A term, IK, KL, LK. So these two cancel, right? And BIL, IL is the same, KL, LK. So these two cancels, and I get a 0. And they've used the fact that the brackets are antisymmetric, which, if you wish, I should have probably stated as one of very important properties. So let me just say Ij is equal to minus Ji. Same with the other bracket. Okay. The Shelton identity is and will be used a number of times. And this part of the sort of very, I would say, elementary toolbox, without taking anything away from that, at some point, you know, you're going to have amplitudes and you're going to have expression. You're going to try to simplify those expressions, and you're going to use this a number of times. Okay, very good. Questions about this? Yes. Yes, precisely. Same. Why is that? Because this also the square brackets are two-dimensional spinors. Other question. These are very good questions. I mean, it means that you're understanding this. Okay. Of their, I mean, you mean in terms of this? Not necessarily, or if you wish, like say, so what you're trying to say is that you want to use two copies of this statement and try to show the same linear dependence for the momentum, but you would have different coefficients in a sense. So like the momenta are not linear. I mean, the momenta are not linearly independent. I mean, the entries of the momenta are not linearly independent beyond the fact that these are null momenta. So to speak. I mean, what you are having, so say that you are using two copies of this, say that you are trying to express momentum J as a linear combination of momentum K and momentum L. You use this would go, I mean, you would have definitely in the expression you obtain a term in which there is momentum J expressed as, you know, something for momentum K and something for momentum L, but there will be an extra piece, an hybrid piece, right, in which you are building another momentum, in which it has the bracket, the angle bracket, sorry, the angle spinor of K, but the square spinor of L and vice versa. So what you would have done is expressed momentum J as momentum K plus momentum L plus two other things. So you're not showing that actually it's dependent. There's this extra thing. And then you work the details of that extra thing, and it turns out, rather uninterestingly, that the extra term is exactly the difference between the three momenta. So this does not imply a linear dependence of momentum J in terms of momentum K and L, as it should be expected, right? Because these momenta as vectors are four components. But that is a very good question. Anything else or a follow-up? Okay. Let me just add a little bit of information on the way for completeness, because I do not know what are you going to use this for. So it is good to know that if we have a real momenta, if you insist on having a real momenta, then we take P alpha. You take the complex conjugate, and this would be equal to P alpha dot. So essentially, complex conjugation changed an undotted index into a dotted index. And same, I mean, for completeness, you also have that this would become essentially P alpha. So this is the conventions I'm using, again, stressing that these are real momenta. And we note that as a consequence of this, we have that if you take a bracket, say PQ, takes complex conjugation here, is equal to QP. So you change the order and you change the kind of bracket. Okay, so this is the first note. The second note is that abuse of notation. I will abuse notation in many ways, but let me be specific about this one particular one. So sometimes, instead of, I will write something of this form instead of a instead of a sigma matrix, and this will be interpreted as the gamma matrix contracted with entries which are either on one side the square and on the other the angle spinor, or zeros. So I will sort of generalize this notation in a situation in which these are completed to four-dimensional object with the remaining zeros. And this is a common abuse of notation. Due to this abuse of notation, one can also write I gamma mu j is equal to j gamma mu I without any sign. If you want to verify this explicitly, you have to remember that, well, in one case, this is understood with a sigma matrix. This is with a sigma bar matrix. You play with the epsilons, and this results in a switch of the two with no sign. Okay, very good. Questions about this? Then there is one important piece of information which is missing to complete a sort of this overview of the spinor-helicity method, namely, okay, polarizations for vector fields. Because so far, we have had a way of expressing with this formalism momenta, spinor polarizations. So vector polarization remain to sort of be able to express all the kinematical data an amplitude will depend on with the new variables. So this is done. I'm over time. I'm not time. Yes. So I think this is done in the afternoon. That's great. So it's. And I'm very sorry. I'm used to finish on the hour, so I didn't realize that there was overtime until now. All right. So we continue this in the afternoon, and yeah, thank you.